Good afternoon to all participants. Once again, we welcome you all to the second session of today's FTP. This session will be led by Mr. Sri Vishnu Damodaran, who is currently serving as an AI solution architect at Data Consultancy Services, Ernakulam, Kerala. With over 7 years of experience in the field, he specializes in designing and delivering end to end AI and data driven solutions encompassing architecture design, model development, application integration, and scalable production deployment. At his core, Ms. Sri Vishnu is a data scientist deeply passionate about uncovering patterns, building intelligent systems, and transforming data into meaningful, actionable insights. Beyond his professional responsibilities, he is dedicated to continuous learning, AI research, open source contributions, and actively sharing knowledge to foster innovation within the AI and ML community. He holds a Bachelor of Technology in Electronics and Communication Engineering from the Federal Institute of Science and Technology. Mr. Srivishnu also serves as a dev expert at Weights and Biases and has been recognized as a Kaggle Top 1% performer. He holds multiple certifications, including Google and Microsoft credentials, underscoring his commitment to professional excellence in the rapidly evolving field of artificial intelligence. Through his expertise and contributions, Mr. Sri Vishnu continues to empower enterprises with cutting edge AI and machine learning solutions that drive impactful digital transformations. Thank you, sir, for agreeing to give us this wonderful session.
Thanks
Over
a
to
lot
you,
for
sir.
the invite. Thanks a lot. Hi, everyone. Good afternoon. Okay, thanks a lot for that great introduction. I think it pretty much covers most of the things that I've done. Thanks a lot for inviting me again. Thanks to all the professors and the coordinators of the event. I hope you're all having a very good learning experience from the past few sessions. And yes, we will continue to do so in this session. And I hope that, at the end of the session, all of you guys I hope that you all get like some very good takeaways, very good insights, um, a lot of inspiration to continue on your journey, right? Because AI is everywhere as of now, and it is not going away. And yes, it is here to stay. And no matter which profession you take, no matter where you head in your career, right, AI is going to be there and is going to be a key part of your lives, even if you're not associated with any technical fields. And even if you are very much associated with any key technologies, if you're working, if you're aspiring to work as in the IT domain, if you want to work as a data scientist or a machine learning engineer or a Gen AI developer or any sort of developer, a web developer, whatever role it may be in the IT industry, AI is going to be there. Okay, so at any point, any of the coordinators or the staff, do let me know if my voice is not audible or if my screen is not visible, because that might cause some issues at any point. And also, maybe we'll take a small break towards the middle of the session. And if there are any questions, we'll keep those questions in mind. And maybe towards the end, we'll discuss all of the questions. Maybe we'll have a dedicated Q&A round towards the end. Okay. All right. So it's great to meet all of you. And it's great to be part of St. Thomas Institute's this session. All right. So let's get started. Okay. So I will share my screen. Let me know when my screen is visible. It will just take a moment. Okay. Once my screen is visible, we can get started.
Yes, sir, it's visible.
Thanks a lot. Thank you. Okay. So today's session is titled Transformers and Large Language Models. And we are going to be demystifying certain concepts, certain ideas, certain models and technologies that is associated with language. And we are also going to be covering some case studies, real world applications, all of that good stuff. Okay. So my name is Sri Vishnu Damodaran, and yes, I was already introduced. Maybe towards the end of the session, if you have any other doubts regarding what sort of work I do, what you can expect if you get into a role similar to what I'm working on, right? See, I started off as a junior data scientist, and then I slowly transitioned as a senior data scientist, and then currently I'm working as an AI architect. I worked on multiple business domains. From there are multiple domains in the industry, right? You can think of multi-billion dollar manufacturing companies, retail franchises, the shipping industry, the logistics industry, um, and predominantly I work for many clients in the US, Europe, and in the Japan geographies. Also, yes, I worked on multiple areas of machine learning and deep learning engine AI as well. So you can think of areas like computer vision, traditional machine learning, where you work just with the relational data. You can also think of this other area, right? NLP, which we are going to be talking about today, right? Natural language processing. I've also done some very good work there, and I've also worked in the past since the past 3-4 years. I worked on generative AI. Ever since the advent or the birth or the AI bloom, it is being referred to by a lot of people these days. Ever since the AI bloom, right, or the Gen AI bloom, I've been working in the generative AI area as well as other traditional AI areas. And also, my work also involves. See, I am just filling out some things which you may be interested in. My work also involves taking these algorithms, right? Not just developing these algorithms, not just analyzing data, but then taking these algorithms, having a data pipeline which connects your real world assets, your real world needs of your customers, your real world data from your customers, from their data sources like databases and data stores, right? Taking that data and bringing it into cloud, and taking your models, taking whatever solutions that you develop in and around machine learning and AI, right? Taking those solutions, scaling those solutions so that those solutions can address and cater to thousands and thousands of users if required. And also those solutions can cater to different aspects of your customers' needs, right? The solution basically has to be production ready and scalable. Okay. So these aspects are also things which I focus on. So if you have any doubts, if you have anything that you would like to ask me, feel free to do so. And I am also hoping to touch upon many of these things today. So that's the reason why I mentioned these things up front. So I will touch upon most of these things today. But then keep in mind that this is a 2-hour session. It's sort of a 2-hour short workshop, you can say. And most of the things that I'll be covering certain things on a high level, but then certain other things I shall try to go a bit in depth. But then, as you know, we are limited on time. We may not be able to go through all of these concepts and technologies in depth. Uh, and also, this session is going to give you a lot of good insights. But then, building upon that, those insights is very crucial. You have to go back, and if you're interested in these areas, you have to go back. You have to spend time. Maybe it might take a few months to get caught up on all of these ideas, learn and work on things so that you are able to, break into the area and create a lot of impact. I'm hoping that as students, I'm hoping that you are all going to be the next generation of people who are going to create this impact. Okay, so let's get started. So I will give a very short overview of the session. So we will go through some crucial basics. Okay, to start with, we will start with some fundamentals that you would need to know to work or to learn about these concepts and technologies. So that is what I will be starting with, some fundamentals. I won't go in depth into these fundamentals. These are things that you would have to note down and go back and learn. Okay, don't worry about these fundamentals being relevant to the rest of the session. Okay, whatever that I will be taking, what I shall do is for some of the beginners. I will try to explain each and everything in a very, very simple layman's terms so that you get an idea and intuition to proceed. And for some of the advanced learners, right, I will ensure that I use some of those terminologies and some of those points and insights for those advanced learners as well. Okay. The beginners who might not be having some idea of these fundamentals, do not worry. You can always go back and learn these fundamentals and then cover the rest of the topics covered in the session. Okay, do not worry. And yes, so the after the fundamentals are done, what we will do is we'll go through some very quick summary or maybe a very quick walkthrough of some of the basics of deep learning. Because we are going to be learning about transformers and large language models, right? We are going to be talking about language models. So we have to know a lot about these concepts, and we have to also get to know a few concepts in and around transformers. Transformers is the key topic of this session. We'll be covering some advanced models as well as we go in depth into this session, right? We'll be covering this model called BERT. Okay. We'll also be covering a very interesting model, which you might already know. It is called GPT. Okay. We'll be covering the principles of GPT, how it was developed, how it evolved from some of the predecessor statistical techniques to where we are today, how GPT itself evolved from version 1 to version 5, where we are now. We'll cover all of that very shortly. And then what we'll do is we will cover some basics of generative AI, just some key concepts. You already know what generative AI is, but then we will redefine it formally. And shortly after that, what we'll do is we'll cover some very interesting case studies. I will show actual code, but just uh, just make sure that you don't try to go through each and every line of that code. I will also not be explaining each and every line, but I will tell you like what libraries I'm using, what frameworks I'm using, how the code is working, all of that flow, the approach that will be covered because we do not have time to cover the entire code. We will stick with this approach, but then you will get a very good feel of how it is done, and you can always go back and learn all of these technologies and do it yourself. Okay, so we'll cover some very interesting case studies, some business implemented architectures. Then that'll be the close of the session. Okay, we'll cover some very interesting case studies at the end. So do look forward to that. Okay, so let's get started. Anything else? Anything that any of the coordinators or the professors here would like to highlight before we get started, or we're good to start? Okay, all right. Let's not waste any more time. If there is anything, do let me know. Do feel free to interrupt me. Okay. So what are the fundamentals? What are the fundamentals that you should know to work with language models, right? To work with transformers and GPT and all of that, all of those technologies, right? How do you work on generative AI? See, what are the things that you should know? This is what I'll be covering first. See, the crucial part of getting to know and working in this area is to know Python. Okay, Python as a programming language is a must. Many of you might already know this. Okay, so I am also assuming some of the audience here would already know Python, and I think a few of these things might already be covered in the previous session. But then do not worry, we'll just go through it quickly. Okay, and yes, Python as a programming language is a must. Now, some machine learning fundamentals. Okay. See, machine learning fundamentals like what is machine learning? What is the idea of training a model? What is optimization? What is inference? What is an optimization algorithm? What are error functions? See, the basics and the idea of machine learning, right? How is it different from traditional programming? So, in traditional programming, you define the syntax, you define the steps, step A, B, C, D, E, right? In machine learning, and you give the input to in traditional programming, you give the input, you get the output, right? In machine learning, what you do is you give the input as well as the corresponding output. You have a lot of these inputs and outputs. Okay, you have a set of inputs and outputs. You give that to basically an algorithm which can learn by itself through an iterative process from these inputs and outputs, and then try to come up with the outputs for the corresponding inputs, right? And then once you do that, the process is called training, and the whole the way it learns, right? These algorithms learns is by minimizing something called an error function or a cost function, and the whole process of minimizing or minimizing the errors, right? Essentially, is called optimization. Whatever algorithm that you use to minimize these errors, for example, stochastic gradient descent, or a greedy algorithm, or whatever that might be used in any of the algorithms. These are called optimization algorithms. And once you have the training done, okay, once the model is ready and has learned from your data, the process of giving it new data and getting the output, right, is called inference. Okay, these ideas are crucial. These are fundamentals. The reason I want you to know these ideas is because I'll be talking about these things and you might get confused. But do not worry. If you're unaware of some of these concepts, I will still, whatever I'll be covering, I will still ensure that I will cover the core idea of whatever I'll be covering. Maybe some of the advanced stuff, you can always go back and learn these ideas. Okay, and then we'll be then you should also know, since you know some basics of ML, right? I'm assuming you will also know classification, regression, some of these ideas as well, classification, regression models. Okay, and then you must also know some deep learning fundamentals. See, right? Models like ANNs, right? ANNs, multi-layer, or it is also called multi-layer perceptrons. Ideas of ANNs and multi-layer perceptrons. What is deep learning, right? We'll be covering a very short crash course of deep learning very quickly, just the idea, but then this is good to know. Then you should also know some ideas and some processes that are done in natural language processing. See things like what is tokenization, what is stemming, lemmatization. Some of these words you may have heard, right? Some ideas in natural language processing, you may have used frameworks like Spacey or NLTK or frameworks like that, right? See some of those ideas, if you know, that'll be very good for the session. And then you should also have some understanding of these models called recurrent neural networks, right? You must have some examples of recurrent neural networks like LSTMs or GRUs, right? If you have some ideas on those networks, it'll be good to know. If you have if you have ideas of all of these things, right? From the session, so one of you who might have an idea of all of these things, you will get the most amount of insights. Okay. Okay, and if you have, it would be very good if you have some idea on transformers. In the previous session, you may have already learned some of these ideas. Okay, and I hope that is fresh in your memory. Then, if that is the case, we are good to start. Okay, if you have some ideas on basic generative AI models, right, that will also be very good. Okay, so in some of these fundamentals, right, any of you, some of these fundamentals, do you feel like you might be lacking in any of these fundamentals, or are most of you already aware of some of these fundamentals? Do you have some? Do most of you? Does the major number of participants here have I think maybe some basic knowledge is probably enough. But then, if you don't have any idea, dude, let me know in the chat, okay? So that I will be able to maybe tailor the session accordingly. Otherwise, we'll also cover some very advanced stuff. Okay. Okay. All right. Okay. So we'll get started with some just the crash course. We won't spend too much time here. Okay. See, what is deep learning? See, deep learning is a branch of ML, right? As you know, you would have learned about ANNs. So ANNs will be able to essentially take care of finding complex patterns from your data. Okay, it is not a very simple model which will be able to only handle very simple logic, maybe with structured data, right? With relational data, with when you have data in the form of just comma separated values, or maybe something like just a table, right? Tabular data. Those are called structured data. When you have to find some logic, or when you have to learn a few patterns and representations in that, then traditional ML would be enough for you. But then if you have to learn from unstructured data, like very complex data, which is difficult to understand, like language, right? See, if you take a sentence, the quick brown fox jumps over the bridge. See, I know the meaning of quick, it's a verb. I know the meaning of fox, it's a noun. Jump, sorry, quick is an adjective. Fox is a noun. Jump is a verb, right? See, I know the meaning of jump. I know fox is an animal. I know fox has is small, looks like a dog. It has a certain color. It has fur. See, I have all of this context. But then your models, whatever that you might be working on, you have to ensure that the model also understands these concepts as an idea of what word it is looking at, what is the meaning of that word, what is the meaning of that word in relation to other words in the sentence. All of this the model needs to know so that it can predict what task that you have to do, right? So that's the reason why with text, with images, with speech, such unstructured data, we have to use deep learning. Okay. And this can automatically learn very, very, very deep and hierarchical features and complex patterns without you doing much to it. Okay. So what is a single layer perceptron? What is a perceptron or a single neuron, right? It has input. I will switch to laser pointer. Just one moment. See, it has inputs. This is the input that we give, right? X1, X2. It is essentially, see, you can think of a single neuron as a um, mathematical function. Okay. Just a simple mathematical formula, a function. Okay. You see, you have your input. You have something called weights. Okay. Just keep these weights in mind. You have something called weights. These are essentially similar to coefficients of your variables in a function. Okay, if you take the function y equals mx plus c, here y is the output, x is the input, m is your coefficient of x. Okay, and c is a different coefficient. Okay, c, these are coefficients. Y, m and c are coefficients. M and c or m and b are coefficients. Okay, y mx plus c, right? M and c are coefficients. See, that's it. So the variables, if you have some coefficients, those are you can think of these as coefficients. And then you have a summation function here. This is basically the linear part of your single neuron. And then you have something called g here, which is a function, which is actually a non-linear function. Okay, it can be represented as a formula, maybe some by using some sort of sinusoidal representation. It can be represented as a formula. It's a non-linear function. Okay, if you can take this whole neuron, right? You can take this whole neuron as a function similar to this. Okay, hw of x equals z1. Z1 is the computer output. Okay, so this thing is z1. Okay, so z1 essentially, or hw of x equals g of sigma over I wi xi. Okay, so essentially you're multiplying weights by x. It's basically doing this operation. Okay, your coefficients are multiplied by your inputs. Okay, and then they are summed over based on how many number of variables you have. Okay, that's it. And then that goes into a function g. See, this g you can think of, if you already know deep learning or machine learning, you can think of as a ReLU function or tanh function or some other similar loss functions. Okay, uh, all right. Activation functions or loss functions. Okay. All right, let's move on. So we have some examples of activation functions. These I think you would already be knowing. Sigmoid, it is represented by this. ReLU is represented by this. You have a hard threshold function. So these are all functions. You can represent it by these curves. Okay, these are essentially what you call nonlinear functions or nonlinearity. So if you combine a linearity with a nonlinearity, you get something called a single neuron. Okay, it is also called a perceptron. That's it. Keep that in mind. Perceptron. What is deep learning? Okay, we'll jump into deep learning. Essentially, if you take that neuron, right, you see this image here. This looks similar, right? Except that it is connected in a web form. If you take that neuron, connect it to form multiple layers, and you give it a bunch of inputs, you increase the inputs. If you only have two inputs, also see that is completely fine. If if you form a network with a perceptron, if it has multiple layers, more than two layers, then it is called a deep neural network. If you only have one layer, it is called a shallow neural network. So a deep neural network is nothing but perceptrons arranged in layers to form multiple layers. If you have more layers, more than one layer, it is called a deep neural network. If you have only one layer, it's called a shallow neural network. See, by doing some research through empirical research, um, we have researchers have essentially found that deep neural networks will be able to capture complex patterns and representations in your data. Okay, that's the reason why we use deep learning. Okay, all right. I hope that much is clear. I hope my explanation was simple. We explained deep learning in 2 minutes. Okay. All right. So just going through some branches here. Okay, going through some branches of deep learning. We have computer vision, where you enable machines to interpret visual data, right? Essentially, your images, text, sorry, images, videos, etc. Videos are nothing but images, split across the temporal domain, right? If you take 24 images, run that through one by one in 1 second, you get like a video, a standard video, right? See, images, videos are nothing but images, videos. If you enable machines or software solutions to understand, interpret that, and give some output or make some key decisions, that is called computer vision. Okay, that is a branch of deep learning. The key idea or the network that we use here is called CNN. Okay, convolutional neural network. And yes, applications are there: image classification, object detection, facial recognition, autonomous vehicles use it, medical imaging. All of this can be done. Okay. So there are tools like OpenCV, TensorFlow, PyTorch, which you can use to learn and develop solutions in computer vision. Similarly, you have something called natural language processing. It is just the other. It is sort of the sister of computer vision, where instead of images and videos, you have text, right? You have text or natural language. Code is also part of a language. Okay, code is essentially a language used to represent an algorithm. Okay, so the field where we understand and interpret and also generate human language, that is called natural language processing. Okay, just some definitions for you all, and we have many applications for it. I'm not going through it. Okay, translation, sentiment analysis, chatbots, summarization, text generation. You can do a lot of stuff pretty much out of the box with your GPT-based models, ChatGPT, and such transformer-based LLMs these days, right? Out of the box. And some key techniques. We already mentioned some of these models: RNNs, transformers. Okay, these are some key techniques used. Tools and frameworks: NLTK, Spacey, Hugging Face transformers is a big library we use. And then, if you want to develop on very, very custom, if you want to do research or develop on custom models, right? Very low level, you can use TensorFlow or PyTorch. Okay, these are some tools and frameworks that we use to learn and develop solutions in NLP and C. Okay, we will continue. So, okay, so let's jump right into essentially this concept of transformers, right? Transformers is what we'll be looking at today. We'll start with transformers. Okay, so I think we will cover transformers very quickly. Okay, I think you must already have an idea from the previous session, but then we'll just cover this very quickly. Just points, refreshing things in relevance to what we'll be looking at, BERT and some of the more advanced models, right? So we'll be covering this quickly. Okay. So all LLMs are transformer based. Okay. GPT, it stands for generative pre-trained transformers. So what are we doing? Just refreshing your memory here. What are we doing with attention mechanism? Okay. What we are doing is we are enabling an algorithm to first of all look at the relationship of one word, maybe in a sentence, with every other word in that sentence. Okay. So essentially, you see this graphic here, right? We form different lines. Each line is having a different opacity or thickness, or you can say the alpha value, right? If it is thicker and darker, it means it is very, very, very closely related to the word that it is matching to. If it is not thick, then it has not a lot of significance. See, this enabling, when we read a sentence, right? The rabbit quickly hopped, the turtle slowly crawled. If you look at these two sentences, rabbit is a noun or the object, the subject of interest, right? And quickly hopped, okay? Very simple sentence. Quickly hopped, adjective, and a verb. See, we are thinking of the sentence and we know what is hopping, what action this rabbit is doing, how is it doing quickly. Okay. So all of these things we know. So the way that we process the sentence in our head is by looking at the relation of one word with all of the other words. Okay. Essentially, we are getting software or algorithms to do the same. Okay. Take one word, get map out the relationship of that, figure out the relationship of that with every other word in that sentence. Similarly, take the next word, figure out the relationship of every other word of that word with every other word. Okay, very simple. And you might be knowing transformers. You have two basic separation or two basic units: the encoder part and the decoder part. Okay, just keep that in mind. Okay, encoder and decoder. It's an encoder decoder architecture. I hope that much is clear. Okay, let's move on. Okay, we'll go through this key idea as well, which is called text representation. That means, see, what we are doing here is, in order to process text, right? I mentioned this idea earlier when we are talking about the sentence. The rabbit quickly hopped. See, these are words, and as we saw in the earlier slides, right? What is a model? It is a mathematical function, right? You cannot give text to a function. Okay, a function, mathematical function, maths basically only understands numbers, right? So you have to take your text, convert that into a numerical form. That is what we are going to do today. Okay, that is what we are going to do next. See, what you do here is, initially you have to split your complex words, which might be having some suffixes and prefixes, to simpler words. Okay, so essentially, big words, if it is a combination of two words, you will split that into simpler words. That process is called tokenization. Okay, keep that in mind. We use certain algorithms like BPE, byte pair encoding, certain algorithms to do this. Okay, and then you have this next process, which is called vectorization, where you convert that word into a numerical form. Okay. The way that we do that is, you take each token, which is only your split words. Okay, just your split words are called tokens. Whatever you see it in different color, these are different tokens. Capes we split into cap and ES. Okay, two tokens, because capes is a complex word derived from a different word. Okay, we change the word into a baser forms. There are also other processes that we do here, okay, like stemming, lemmatization, stop word removal, all of this process. Um, yes, I suggest that you go through this process by learning some NLP basics, okay? So these are not important. Those are not the primary idea of what you will be explaining. So I won't go through these things, okay? But then please do ensure that you learn the idea of these things. See, the vectorization process, right? It takes each token. Essentially, king and queen are tokens. Not is a token, all is a token, heroes is a token. You take a token and you represent that in an n dimensional space. N dimensional space. Okay, a space having n dimensions. This, what you see here, is a three-dimensional space. This having two axes, right? X and Y. It is a two-dimensional space. If you see, the way that we represent these words in an n-dimensional space is by using a different model or a technique to represent that word, and in a space where the distance or the position of that word, right, has meaning. Okay, so everything in that space has meaning. See, math is here, mathematical is near it, linguistics is related to mathematics in some way, so it is here. This link might be the link, is what represents the relation of linguistics with mathematics. Students are here, teachers are here. This is the link between students and teachers. What is the link? Teachers teach students, students learn from teachers. So this vector, if you take a vector here, that is that link. Teaching, taught, learn, learned. See, you have all the words represented in a space. Everything in that word, every position has a meaning. For example, let me tell you, if you take two words, okay, king and queen, you have the vectors. You have these vectors, right? If this is an n-dimensional space, you have multiple values in an array. So if it is an n-dimensional space, it will have n floating point numbers in this array. If you take these two vectors, to simplify things, we are representing these two vectors as 2D, okay, just two dimensions. If you take these two vectors, okay, so you take king, okay, and you have these two other vectors as well, man and woman. If you take king, if you minus the man part, this vector from king, okay, you take king and minus man from it. If you add women to it, add women to that, right? King minus man plus women, you'll get this vector queen. See, that is how this space is modeled. And the whole process, taking your words, converting into these floating point values for each word, where which is it represents a space where words are modeled, right? That whole process is called vectorization. Understand that? Keep that in mind. We'll move on. Okay. So this is actually where it does it. Okay. All right. So we'll just have a quick look at how it is done. Okay. 1 second. I think if you're having some bandwidth problem, what I'll do is I'll turn off my video. Just hold on 1 second. So far, I'm hoping that you guys are all not having any audio issues. If you have any issues, do let me know. Okay. Okay. So you have your input here, right? You are taking a simple sentence here. Hello, how are you? Okay. And then what are we doing? We are tokenizing it. See, we are tokenizing each and every word, maybe splitting complex words. Some of the punctuation, like commas and question marks, these are also tokenized. Okay, we split that into tokens, we get an array essentially. What you do is you do this process. In here, you do this process called numericalization, where you map each word to a number based on a corpus, basically a dictionary. Okay, corpus is essentially a dictionary where you have multiple words, right? So you take this corpus where you map it into numbers based on a lookup done on a corpus. Okay, what you do is you take each word now and pass it through this function e of that word, right? E of that word essentially gives the vector of that word, vector embedding of that word. This is called embedding. You get the embedding for hello, how, are, and you, and also for these commas and question marks. Okay, as you see here, this is an n-dimensional array. Okay, and see emb dim, that is our dimension, or you can just call it n for the for simplicity. Okay, and what are you doing? Now you're stacking it. You just stack it. I'll move this away. And then you do this process called padding. Okay. Similar. This is done. Okay. Typically, this is done to ensure that, most models that we work with today, right? They have a fixed input size. Models, whatever input that you have, you cannot vary it every time because it is trained on a fixed input size. You have to ensure that the input size of whatever sentence that you have also matches that size. Okay, typically it can be 256, 512. A lot of LLMs these days have a very big context size, like 128,000 or 10 million is also context size of one of the recent models. Okay, here this is 9. Okay, if it is 9, what we do is we add the special tokens. Whatever you see throughout the entirety of the session in this greater than less than sign, right? In between that, those are called special tokens. It is essentially a number, an n-dimensional array, okay, which represents that function or some operation. Okay, here to indicate padding, it is given this. Okay, if you train a model by doing this, we just teach a model. Okay, that this value represents padding. Okay, that is it. This value represents padding. If you train a model over and over again, it will learn that okay, if I see this token, it represents padding. Token, this padding token, special tokens will also have a n-dimensional set of values. It will be an n-dimensional array. Okay, essentially that is what you do. Okay, now you get this final thing. See, I'll move on to the next slide. Second. Okay. See, now what you do here is you stack it again just so that we can see all of this here. See, padding is represented like this. Okay. Now you do something called positional embedding. I think you already learned about positional embedding. It is essentially helping you to preserve the order of the words. Okay. When you give a bunch of input to a model, you need to tell the model, especially in models like transformers, right? You lose track of the order of words because you'll be taking each word, looking at every other word. Okay. So what you do is you take the vectors. These are basically mathematical values, right? N-dimensional arrays. You take those vectors, pass it through, multiply it by a different function. And here we choose to multiply it by a sinusoidal function representing the order. Okay. If it is the first word, you give a sinusoidal function this one value. It is a specific function which basically you use, and you compute the value of that sinusoidal function, multiply it, okay, to your vector. So essentially, all the numbers in that vector get multiplied that function, and that essentially makes your model understand that okay, hello is the first word, okay, and the rest of the words, okay, it will tag it basically. That the way that we do that is by using this sinusoidal function, multiplying it. That whole process is called positional embedding. Okay. Then what you do here is you get this matrix finally. Okay, you get this input matrix. So that is going to go into your encoder block of your transformers. Okay, that is going to go into your input. Okay, all right. So we just saw flow with some sample data of how things get processed. Okay. Now we'll jump into more of the details of the session. One second. We'll jump into this particular slide where okay. So that is what goes into this here. Okay. See, as you see here, we compute the embeddings, and then we do positional encoding where we multiply the sinusoidal function with our right. That is done, and then that goes into these other sections in this slide. So what all do you have here? One second. Okay. So you have the encoder here. What is represented in red? What is represented in the next box you see here? That is your decoder part. Okay. So how does transformer architecture work? You have your encoder. You have multiple blocks, NX blocks of these encoder, right? Where it is having multi-head attention. You do adding a normalization, and then you have a simple feed-forward network. Or you also saw this earlier. It's basically an ANN, okay, or a deep neural network. And then you do adding a normalization again. That so this is the encoder part, and then that goes into this decoder part where you feed in the outputs shifted right here. See this particular model, right? This is called so whenever you give inputs, right, you have to feed the output back to this decoder part. This is where you get the output when you give in. We'll see this, okay? We'll see this in working. When you feed word by word into this network, when we can feed in whole sentences here, okay, to start with, it will start producing each word by word, okay. Yeah. What are LLMs? What are these sort of transformer based models doing? It is predicting the next word, right? So the next word gets predicted here. Once you have one prediction, you need to feed the outputs back here to this decoder part, okay. And this whole way of doing things is called regressive modeling, okay. And yes, what we will do here is here the output is again combined with the input sentence. Each word of the output is again combined with the input sentence by using something called cross attention. Whatever happens here, we are taking a look at this input sentence, comparing one word with every word in that sentence. Okay, input sentence. Here, what we're doing here is in the decoder part, we are taking this particular representation. We are taking a look at that with every word in the output as well. Okay. And that essentially ensures that we are also paying attention to the output. Okay. And that is how cross attention. What you have here is called self attention. If all the branches of attention goes into one block, that is self attention. If you have two blocks coming in here, if the what is it the key and value, right, if the key and value are different from the query, okay, key and value are different from the query, then you have cross attention. Okay, if everything the same, query, key and value are the same, it is called self attention. So this whole attention mechanism is derived from searching methodology, where you have query key and value. You find the based on the queries, you find the values, and you also have keys, okay, which helps you to find the value. Okay, it is based on that whole idea of searching methodology. Okay, so this is a formula for attention. May have already seen all of this, right? See, there are a few types of language models also, which we will look at this slide. Okay, I think. Okay, one second. Okay, so they are encoder only, encoder decoder, and decoder only. See, encoder only contains only this encoder part, just this encoder part. Okay, so there are language models which are encoder only. For example, BERT is one, which we'll take a look at today. Then you have encoder decoder models, which an example is BART. Okay, and then you have decoder only models. Most of your GPT models, most of your large language models these days are decoder only. You only have this part. Okay. All right. So that these are all different types. Okay. And essentially, encoder only models are used for sequence to sequence task. One sequence, one sentence to a different sequence. Encoder decoder models. Here, the only thing is sequence length, input sequence length is not equal to output sequence length. Here also the same thing, decoder only also input sequence lengths need not be equal to the output sequence length. I think you will understand this later as we go in depth into the model that we will look at today. Okay. All right. Let's take a look at our model that we'll be. Let's take a look at this model called, one second, bidirectional encoder representations from transformers. Okay. So in short, it is called BERT. Okay. So BERT is is the state of it was a state of the art NLP model. It was introduced in 2018, and at the time, a lot of language tasks were done with this model. It showed great performance across a wide variety of NLP tasks. Okay, the reason why this BERT model has these sort of nature is because it can understand context in both directions. As in, it is an encoder only model. Okay, think of it. It is only having that encoder in the encoder decoder architecture. So, as you see here, right, you see this schematic here. It is having NX or N, okay, number of encoders connector. And you can essentially feed in your sentence here. Okay, whatever you see in class as this class thing, right? It is something called it is essentially the same thing which I mentioned earlier, special token. Okay, here it's something called a classifier token, which I will explain shortly. So BERT can look at language from left to right and right to left as well. See, the reason why this works is because left to right and right to left is also some the way that we process language in our head. Okay, sometimes we look at sentences from right to left as well. We don't simply look at sentences from left to right. Because of this reason, it captures richer context from your text. Okay, and what is the principle? We'll be going through the principle of BERT, right? So, what are the key principles of BERT which sets it apart, which gives it that state of the art performance, right? Two things, very simple. Two things. One is called masked language modeling. The next thing, it is called next sentence prediction. NSP and MLM. Okay, masked language modeling and next sentence prediction. So BERT essentially use these key techniques, which these are called novelties. Novelties means essentially um, see, see what are the different see here you have some innovations brought in by the researchers of BERT, right? See what are the different things which they introduced in their paper, which helped in improving this model. That is essentially your MLM and NSP here for BERT. So we'll cover these things in depth in the next slide. Okay. So BERT excels in a lot of different tasks. You can use it for translation, question answering, sentiment analysis, summarization. You can also use it for any or a lot of different tasks. Okay, if you fine tune BERT for different tasks, you can use it for many language tasks. We'll take a look at how it is different. Okay. Okay. So we have in this slide base essentially what we are looking at is before we explain about the novelties of BERT, we'll look at what were the problems associated with some of the previous models. See, some of the previous models, they struggle with something called long-term dependencies. The problem with long-term dependencies, I think most faculties here would might be knowing this because if you know LSTM or GRUs, most faculties would know. Long-term dependencies mean when the sentence get longer, these models will not be able to capture the meaning of the first word in relation to maybe some of the next after a few words in the sequence, right? Maybe some of the later words, it will not capture that relationship. Because of that, this was a problem. It was solved by transformers, and with BERT, it was again solved in a better way. And the other idea or the other idea which set this model apart is the transfer learning capabilities, where specific language tasks can be solved with NLP, with BERT, with transfer, this technique called transfer learning. And what you do here is by doing a very unsupervised, large scale learning process called pre-training, we just feed in a lot of text to these sort of models, and they learn from this text. That whole process is called pre-training. We will go through this process, and shortly after that, what will happen is we will do some another different process called fine tuning, where we take just small amount of data for a very specific task that we have to do, and then we train that already pre-trained model with that specific small data set to do the task. Okay, so that whole idea is called transfer learning. And when this was done with the BERT models, they showed a lot of performance, very good performance with many NLP tasks. And yes, then this bidirectional context understanding, this was also a novelty. Okay, so we'll jump into what masked language modeling and next sentence prediction is doing. Okay, so essentially with masked language modeling, it is self-explanatory. Whatever is in that phrase, right? Masked language modeling. What we are doing here is we are taking a sentence. Please divert your attention to the top right of the screen. We are taking a sentence here, and we will mask random tokens, or we will mask the final token in this particular sentence. We will mask final token in with respect to BERT. This is something that we do. Sometimes we will mask um, the middle token or some other token because BERT is bidirectional, right? In BERT, we can mask any word towards the middle of the sentence. But with some of the next models that we see, which is encoder only, which is unidirectional, we will not mask the middle word. We will only mask the final word. Okay, so we'll mask this. These middle words, and then what we'll do is essentially masking is essentially turning those values into a constant value. We will feed this input into the BERT model from left to right and from right to left, and that essentially we'll try to predict this mask, right? Whatever is in that mask, we'll try to predict it. See, if you see this input, my friend likes the movie, my friend dash the movie. We'll feed the sentence from left to right, ask it to predict. Okay, if I am looking at it as a human, I have a few options in my mind. My friend loves the movie, my friend likes the movie. These are all possible words, right? That is also what the BERT model does. That is how we are teaching this model to understand language. So this is done as a large scale process. We will go through it. Similarly, we will also feed in the data in the reverse direction, where movie, the dash, friend, mine. We also sometimes look at read sentences from right to left, just to fill out this word. Doing that also, helps us to understand that here the possible words are likes, loves, hates, some words like that, right? Okay. Similarly, BERT does the same thing. So the way, so what we do here is we have a large data set, and in that large data set, we randomly mask these sort of words, and we ask Bird to predict it. And when we talk about large data sets, we'll talk about large data sets shortly. We're talking about, um, let's say, billions of tokens of words, sentences, data, essentially from articles online, websites, code, Wikipedia, all of these sources. You take all of that, do this sort of processing, and then you just give it to a model and ask it to do the pre-training by following this process, right? Fast language modeling. The benefit of doing that is that your model, after that heavy process, that long process, it will try understand. You'll get a grip of language. Okay, and yes, the next idea essentially here is next sentence prediction. So next sentence prediction, essentially what we do here is it trains the model to decide if one sentence is related to another sentence. We talked about that special token, CLS token, right? See, that also applies here. See, CLS token, class label you see here. You give, see, into BERT, typically what we do here is with respect, by using a separator special token, we always feed two sentences. Okay, we always feed two sentences, and every time we give an input, these two sentences to BERT, we try to predict the probability of the first sentence being related to the second sentence. Okay, that probability, right? So we take a lot of data. We ensure that when we sample our data from this large data set having billions of tokens, we sometimes 50% we take related sentences. If second sentence follows this first sentence, we take that. 50% sampling is done like that. 50% we take two sentences randomly across that entire data set. We form a data set like that. 50% two sentences are related. 50% of that entire training data, two sentences are not related. We make a very quick and dirty labeling like that by doing this automated process, and then we feed it into this model. So by doing this, predicting this class token, the probability of these two sentences being related to each other, right? The model also learns to improve its language understanding. Okay, enhancing its capabilities, enhancing its relationship understanding abilities. And then the next novelty here is both of these tasks. There is always a class token output in the output of BERT. Okay, both of these tasks are jointly optimized. Means essentially you have two error functions will be there. You jointly optimize it by using an arithmetic operator. Okay, just by doing just optimizing both of these things by forming a combined metric, right, with both of these error functions. That essentially ensures that this BERT model. So after doing this training and following this whole process, people, researchers have found that these models can understand language a lot better. So we'll talk in detail about this pre-training and fine-tuning process. Okay. So essentially, what is pre-training? Pre-training means we have a large corpora, and what you do here is you take these sentences as you see on the top schematic here. Take these sentences, mask sentence A, mask sentence B, and you also have this class token and everything here. Okay. We feed it in. These are unlabeled, and what you do here is you try to predict the class label as well as the masked words, right? And then you do it on a huge set of data, just randomly, because there is no manual annotation or labeling involved. Humans need not spend time in labeling these billions of words, data set having billions of words. So we just feed it in, do the training, and that whole process is called pre-training. Then what you do here is BERT is also fine-tuned on a few data. See, this is Squad is a question answering data set. This is an NER data set. So we also take multiple specific data sets for different tasks, which is already existing, and then we do fine tuning with that small data set. Whatever we get, the model we get out of this pre-training, right? Already this will have a very good language understanding. We just do a very quick and dirty fine tuning process where we train it for a short time and with short amount of data. This then the model will be able to do it. Okay, that whole process. This final process is called fine tuning, and then what we found is that this reduces the time that it takes to improve the performance. So see, the we'll talk about this, okay, this pre-training fine-tuning methodology later on, but then essentially the reason why we do this is because um, we get a generic learner we get out of this pre-training process, and that generic learner can be adapted very easily to downstream specific tasks. Okay, that's the reason why we use something called this whole process. We don't need to train on billions of words again for a small task. We can use the generic learner to a quick fine tuning to do that specific task. See, we talked about MSM, MLM, mass language modeling, and then we talked about next sentence prediction. Both of these novelties, and also the joint optimization aspect of it, then the fine tuning aspect of it. These five things are essentially the principles of BERT. These five things are done in the paper, and the researchers have done this, and then they tried and tested it out. They evaluated this model in multiple data set, and it showed very good performance. Okay, it was in 2018, 19, even in 2020, BERT model was used for most language tasks and numerous other models, right? Numerous other models based on BERT, right? Robert, Roberta, Distal BERT. Numerous versions came out which improved this BERT again, which improved the size of the models. All of that was done. Okay. Now that covers the principles of BERT. If you have any questions, do let me know. BERT is a very interesting model. It is very interesting to look at the internal workings of this model. Now we'll jump into a different model. Okay, it's called GPT. You already know this generative pre-trained transformer, right? See, if you understand BERT, GPT is actually very simple. There is nothing to explain in GPT. Okay, if you understand transformer and BERT, there is actually nothing to explain in GPT. We will just explain GPT in 2 slides, I think. Okay. So GPT is an auto-regressive model, as in it predicts future values based on the past values. It is not predicting anything in the middle anywhere. Okay, it is predicting sequentially. Next word prediction is what is being done. Most of your large language models, ChatGPT, your GPT-4, GPT-3, GPT-2, your Llama, Gemini, these are all next word prediction, auto-regressive, decoder-only models. Okay, we will talk about large language models, but essentially here we'll talk about GPT, which you can consider maybe a semi-large language model, GPT, the first version, and from GPT-2, 3 onwards, you can call it large language models, perhaps. So essentially, as you see here in this particular image, right, recite the first law. We are talking about the laws of robotics here, okay? If I don't know if you have seen or if you are aware of the laws of robotics. Essentially, a robot may not harm human. It goes something like that. Okay. So recite the first law. So what is the next word? Okay. So whatever is in red, right? That is what is being given to GPT. So as I said, it's an auto-regressive generative model, right? Auto-regressive generative decoder only model. Okay. Recite the first law. Then it produces the token A. Okay. That is the output. Then that A is fed again into input. Okay. Produces robot. Robot is again fed to the input. This whole thing goes to the input. Okay. And then it produces May. May is again fed to the input to GPT, and it produces not. Goes on and on like that. Okay. That is how auto-regressive generative models work. What is the architecture? Here we have it on the right. It is essentially nothing but the decoder of a transformer. We have 12x blocks here, 12x blocks of this decoder attention block. That is it. It is doing masked multi self attention, layer normalization, feed forward network is there, which is nothing but a multi-layer perceptron. You have an addition operation, you have this layer normalization again. Then it is, we can split it into multiple tasks. You have your text and the positional embedding happening. Okay, all the embedding is happening outside here. You have 12 blocks. That is it. The first GPT was nothing but this. Okay. Now, what is different with GPT? How is it different with other models, right? This is nothing but transformers. How is it different? Why is it giving us very good performance? The reason for that is because of these two things. One is called pre-training. Essentially, the next thing is called fine-tuning. We already saw this, right? Pre-training and fine-tuning. How is it different for GPT, right? So for GPT, this pre-training and fine-tuning was done as a process called generative pre-train. As the name suggests, right? Generative pre-trained transformers. Okay. Generative pre-training is the process done which sets this model apart. It is nothing but a scaled up version of a transformer. You have 12 blocks of the encoder there. And what you're doing here is, what is different here is to build the foundational understanding of language. We are doing that essentially that same process that we mentioned. Enormous data is taken. The data was scaled up to a very, very, very large extent, and enormous data from books, websites, all of these articles online, all of that was taken. By using this data, we just feed it into the model, try to predict the next word. That's it. Okay. Next word, word by word by word by word, again and again. We just do this iteratively, ask the model to predict it. Okay. We do this repeatedly on a large scale on this big model for a very long time on a pool of GPUs, interconnected GPUs. We optimize that model, the weights or the coefficients of that model, and at the end of that process we get like a very good generic task solver, generic natural language task solver. And this task solver has a lot of language understanding. It has a lot of language understanding. It can do a lot of language tasks. It also has a lot of information. It has a lot of memory as well, because it has been trained on this huge volume and a variety of data, right? Okay, so then we do this process called fine tuning, right? Here, fine tuning, the same thing. Okay, some of the GPT models essentially earlier were fine tuned to adjust or align the weights on certain tasks like question answering, summarization, translation languages. And the way that we did this is, I'll explain. I think in the next slide we'll explain that. See, the way that we did this is by using, is to teach the model how to use these special tokens. Okay. Initially, this was done initially. Okay. If you want to translate this word from English to French, right? We do fine tuning with the pairs of English and French translations, and then we use a special token. And essentially, training the model on with this data makes sure that, okay, if I pass in the special token after an English sentence, it will convert that English sentence into French. Similarly to multiple other languages. That was how GPT one of the initial models of GPT were taught to do translation. Similarly, if you want to summarize, first set of sentences are given, the second sentence will be summary. Okay. Similarly, so if you pass in this summarization token, in the next, whatever it predicts next will be the summary. See, it will not be whatever is in the input, right? It will not be just one sentence. Okay, it will be multiple sentences. Whenever you pass the summarize special token, it will be an n-dimensional vector, a specific value. If you're teaching it through training, you teach it, right? Whatever values you want to choose, you can choose. Okay, but then if that is chosen, because in the output when we do the training we will pass in the summary only, right? This is all supervised. By passing the summary only, the model learns that, hey, if I see this special token, I have to either translate this. If I see this token, if I see this token, I have to summarize. Okay. By using these special tokens, we did the what is it? We did something called task-based fine-tune. Okay. Now, the next, just one thing. Okay, just one thing which is different in GPT in comparison to BERT and other language models and transformers, right? It is called masked self-attention. That is the only thing that we saw in the previous slide, which is different in this architecture. Instead of multi-self-attention, multi-head self-attention, we have masked self-attention. Okay. The reason why we have masked self-attention is to ensure that when we do the training, the in the sentences, right, the model does not get to see the other words. It only sees the words in order from left to right. So to do that, what we do here is we take the queries, we multiply those by the keys, we get the scores before softmax. You must know that this is what happens inside the transform attention equation, right? Queries are multiplied by keys. Do the softmax of that, and then you multiply that by the values. So similar to that, when we before we do the softmax, we do a masking. We do a masking of these tokens essentially by using a function, and that masking ensures that the words towards the right, they are masked. Okay, so the model does not see the weights or the values for the relation of one word, any word which is on the right of any words. It does not see that relation. Whatever words on the right, they only see the word, the whatever is on the left. Okay, whatever is on the right, that relations are completely zeroed out. Okay, and we get a softmax score like this. So that process is called masked self-attention. This is to ensure that uh, the model only looks, if you have a word, it only looks to the left side. It will not look to the right side. Okay, I will explain it just 1 second. See, in this sentence, if you take law word, the weight of that word, the importance of that word with other words are only taken from the left side. Okay, law importance to recite is captured, law importance to the is captured, law importance to first is captured. Law importance to this token is not captured at any instance. For the word the importance to recite is captured. The importance to first or law or this token is not captured. So that is called masked self-attention that is used in GPT. Those are the only things. Masked self-attention and pre-training was already done, right? Already done in many models, but all of that. So pre-training, masked self-attention, task-based fine-tune. These are the three things done in GPT, which these are the three novelties. That is what enables GPT to solve all of these great tasks with very high performance. Okay, we'll come to generative AI. We'll very quickly cover a few slides on generative AI. See, we will go through, I think, in one of the upcoming sessions, you will see generative AI in detail. But then here, essentially, generative AI is nothing but your GPT, right? GPT-like models with some small variations depending on the vendor, whoever the service, which the company which trains these models, they bring their own small changes in the architecture. What they do is you just scale that model. Instead of in GPT-1, you had these 15 layers or 12 layers or something. Instead of that, you make it into 100 layers. Okay. And what you do here is you also scale on the data, on the model size or the number of parameters. The number of parameters are nothing but in that model equation, what are your coefficients, right? Those coefficients, those number of learnable parameters, you scale that, you make it higher, and then you also have the data, right? You take that, make it higher. You do this to a GPT model, you have GPT-3, okay, one of the large language models. That is it. And what you have noticed is that by doing this, you have just found generative AI. These models, they are able to generate content very well to beyond human level intelligence. It is a benchmark in AI, right? Beyond human level intelligence. Now, most models are better at creating language, writing English or other languages in comparison to me. I know English and I know Malayalam, but most LLMs are better than me at language. But LLMs also know 100 other languages which I don't. Okay, So linguistically, LLMs we have crossed in the area of research. We have crossed in the task of language modeling. We have crossed human level intelligence benchmark. Okay, it is a big feat in this area. Why is GenAI so popular? Okay, so it is giving out of the box without any fine tuning. We can solve a lot of tasks just by describing to the GenAI model. We can also fast track the development of many applications with these models. These are general purpose. You can use it for multiple purposes, whatever you want. And this has disrupted a lot of businesses. This is the reason why Gen AI is popular. Okay, so we'll take a very quick look at early statistical. How it evolved, right? These language models. See, these language models, they started with essentially they started with specific task solvers like some very simple statistical models which just predicts the next probability of the next word in a sentence, okay, given a few initial set of words. So we started with models like ngram models, and then we got the next breakthrough in this area, right? Next breakthrough was word embeddings, which we saw today, right? Word representations or word embeddings enabled us to capture the complex patterns and representations of language and the relationship between words. So more algorithms like word to vec, you have glove, you have many other algorithms which helps us to model words or represent words. That was found, which improved the field. It was a big breakthrough. Then we had a transferable NLP learners, basically transferable NLP task solvers, which required this paradigm called pre-training and fine-tuning. This whole process of transfer learning, right? Where we pre-train in a very unsupervised way on a large corpus of data to give it language understanding. We saw that today. And then what did we do? We did fine tuning on specific data of whatever task we want, and then we made that model work. So examples of that is BERT. See, BERT, GPT-1, 2 are all what do you call transferable NLP task solvers. It out of the box, it is not able to do tasks very well. Okay, but then you have to fine tune it. Then what did we have? We had general purpose task solvers, starting with the invention or the inception of Gen AI, where you have GPT-3, 4, ChatGPT, Claude, Gemini, all of these good models. What are they capable of without any fine tuning? Out of the box, you take it, you can do a language task. You just describe the task to it, you do proper grounding, and then you can do a language task. What happened? How did we achieve this? We'll see it in the next slide. Okay. The way that we achieve this is by scaling the number of parameters as well as the data. So here we have a metric which shows the linguistic ability and the understanding basically on a data set, right? Of these LLMs. Whatever you see as a big dot, the higher the size of the dot, the higher the number of learnable parameters. See, our idea always is to reduce the number of parameters, but make it reduce the number of parameters, at the same time make it more able to solve the task or make its linguistic ability or understanding better. So that this graph essentially summarizes that, and we have multiple models here, right? We started out with GPT-3, we had GPT-1 and 2 before this, okay, but then showing only LLMs here. Now we are at O1 and models like that. Gemini O1, Gemini 3 will come around here somewhere, okay? So essentially what you're doing here is you have a GPT-4 and such models also somewhere. Essentially, what you're doing here is with time, what we did was we reduced the number of parameters. At the same time, we have exceeded human expert level intelligence, and we are able to have a very high linguistic ability by reducing by having a small model also. Okay, so this essentially shows that. Okay, so the way that we did this is by using a large amount of data as well as increasing the size of the model. But then ultimately we have to reduce the size of the model also. It should not be very big. See, these models, GPT-4 Classic was very big, but then it was very good at solving tasks at that time. But then it was very big. So we struggled because the cost associated with these models was very high because it needed a lot of GPUs. It will expand in the memory like crazy, and then whatever input that you feed to it, it will take a lot of time to compute the output as well because the latency was also high. That is bad. Okay, and the support of hardware also is difficult for you. You have to find big hardware to host these models. Okay, only the big players can do it. So this is what we have done. This is where we are. What is the current landscape of LLMs? Okay. Essentially, you have the progression of GPT here. So in GPT-2, we had 1.5 billion parameters. In GPT-3, we had 175 billion parameters. We increased it. In GPT-4, have not revealed the parameters. Okay. I think we get the parameters, but then they have not revealed anything about the data. Okay. And also in GPT 4.5, also they have not revealed the number of parameters or the data. GPT 4.1, it has reduced in size most definitely. Also in 5, the model size or the parameters has reduced, but the ability has gone up. Okay. So the difference with GPT 4 until 5, there are a few key differences. One difference is that we did not just train with text, we train with images and audio and other data types as well. And such models which can handle multiple types of data, that those models are called multimodal. Okay, multimodal models or multimodal LLMs. The word model is spelled MODEL, but then this model, the word model is spelled MODAL. Okay, multimodal means it is related to multimodalities. By modalities here we mean multiple types of inputs. Okay, multiple modality supporting models are models starting from GPT-4. Okay, and that is what enables us. Okay, we can also feed in images to LLMs these days, right? And it will understand it. So it was not just trained on LLMs, sorry, text, but then we also included VIT, visual image transformers. VIT is a specific architecture. It is a combination of CNNs and transformers by combining the abilities of both. You can take a look at this architecture. Essentially, using this, we have dedicated blocks which does the processing of images by splitting the image into tiles and tokenizing it, and we make these LLMs understand the images as well. Okay, by following that generic pre-training process, generative pre-training process itself. Okay, so that is the background and evaluation. See, I will take a very quick moment here to talk about cloud platforms as well. Here, we will require cloud platforms for any of your applications that you do. See, we are close to the slide, the topic where we talk about case studies. So the reason why we need cloud is to scale your applications. And if you take an example here, if you take Azure, right, you can cost effectively scale, and it offers a lot of managed services so that you can focus on the problem rather than focusing on the hardware configuration, management of the hardware, downtime of the hardware, the power to give to the hardware, how to manage the memory and the RAM, all of that, right? You get managed services which you can use out of the box. You don't need to worry about hosting it. You don't need to worry about updating it, all of that. Okay, you can focus on the problem. You pay for what you use. You have past services. If you take here, you have Azure AI services. It is a set of services from Azure which offers you LLMs, which offers you models, which helps you to fine tune LLMs, which offers you out of the box APIs for vision related, language related tasks to do a lot of things. The benefit of these services is that you can scale your applications for your business needs, and you can very easily develop solutions quickly. Okay, so these are some of the benefits and the reason why you need cloud platforms. We just introduce Azure quickly. Okay, all right. We'll get into case studies and real world applications. Before that, what I'll do is we'll take a very quick break. We don't have too much time, but then 5 minutes is what we will take as a break. And then what we'll do is we will look into a quick case study where where we'll look into the working of BERT. Basically, how we get BERT to do a task. Okay, we'll do a deep dive there. Then we'll talk about this concept called RAG. Okay, what it is and what we do with RAG. And then after that, we will do a very quick walkthrough of a solution which covers RAG, basically a Q&A chatbot. And then we'll look at an architecture, basically an actual business case implementation, a sample of a business case implementation, which we deliver to our customers. We'll take a look at that based on Azure. And then we'll look at a very niche or a cutting edge solution implementation, which is basically doing something called agentic RAG, where we use AI agents. And we'll do also something called layout processing or layout analysis. That'll be the end of the session. We'll take a quick break and then we'll cover all of these good topics. Okay. In the quick break, if you have any questions, do let me know. If you need me to cover anything in the upcoming time, do let me know that as well. If you have any doubts or anything you would like to ask me, do let me know. We'll just take quick minutes and reconvene here back at 3:37. Okay, it's 3:32 now. Hi everyone. Hello. Good afternoon again. I hope my screen is visible. I've shared this screen. So I think we are all back and good to start, right? Okay, if you're all back, if most of you is back, maybe you can give a react, maybe react to this, or should we wait for a couple of minutes? Okay, I think Miss Pooja, if you're there, can we start? Okay, good to start, right? Okay, great, great. All right. So, okay. So the first case study that we'll be covering is we will cover very quickly how we can use BERT. Okay. So what I'll do is in the code, since we only have, we don't have not a lot of time, we have to cover a few other case studies as well. We will cover maybe just the very basic flow of this. We will talk about what tools you can use, what are the different techniques you can use. All of those things alone. We won't go through every line of code as I mentioned initially. Okay. Just give me 1 second. There is some server issue with. Okay, no worries. All right. So to start off with, in this particular code base, we will use couple of libraries. Okay, you don't have to worry about all of these libraries. These are for charting and such purposes. We'll use pandas as a data frame processing tool. We'll use NLTK library to tokenize, to remove stopwords, all of that process. We'll use Spacey for a few internal just NLP operations, predominantly as the primary tool for implementing or for working with BERT models. We'll use Keras here. Okay. And then for some metrics, we'll use Scalar. Okay. Just some metrics to view the scores of these metrics. Okay. These are some libraries you must learn to work with these models. So the problem, let me explain the problem to you. Okay. We'll do something called disaster tweet classification. Okay. And this is essentially sentiment analysis through this classification task. We, what we do here is we classify tweets. Essentially, if you know Twitter or X, you have posts are called tweets, and they're essentially messages or social media posts. They contain a bunch of words, basically sentences or words, whatever you want. You can put paragraphs. They have a word limit as well in Twitter, and you have to classify that as disaster tweets or not. Okay. Essentially, what that is it a genuine disaster tweet or is it not a genuine disaster tweet? Are they talking about something else? That is what we are being doing here. Okay. And what we are doing here is I will skip a few of this data EDA part, data exploratory data analysis. You can go back if you're interested and look at these things. And we'll take a look at this data. Okay. So as you see the data, some data points here, right? Free entry in a 2 weekly comp to win FA Cup. This is related to football. Okay. These are all tweets that is not related to disasters. Okay, we can read from it. So here we are doing some data pre-processing where we are cleaning the corpus. And essentially what you're doing here is we will do stemming, we'll do lemmatization, where we change words into the base forms. We will remove stop words. These are words without having any information in it. according, if you have learned information theory, um, any words, some words does not contain any information, like certain prepositions, certain words. These are not required with some of the earlier models. Some newer models, they take in these words or these tokens as well. Tokens without information, they are removed. Okay. And we also, certain models are lowercase only. So we change all the characters into, if they are in uppercase, we change it into lowercase. Okay. And similarly, we do lemmatization to change words into their base forms. And we do tokenization. That is done here. Okay, I'm not going to cover it. We have already talked about it in detail. And here we are doing word representation by this technique called TF-IDF. You can also, we are also using, okay, later on, we also have techniques where we use glove-based tokenization. We talked about tokenization, right? We won't go into that. See, then we will come to words, BERT. Okay. See, we already explained about BERT, and you can import BERT directly from the tokenizers, the Hugging Face library tokenizers. And this is essentially your Hugging Face library where you're using BERT. Okay. So BERT is the, so for some of the other models here, we are using Keras, TensorFlow Keras, but for BERT, we are taking it from Hugging Face Transformers library. Okay, that is an additional library. I missed that. I missed to mention that in the beginning. Sorry. Okay. So for BERT, we are using Hugging Face Transformers. We get this BERT large uncased model. We also have a BERT small as well, and that we are loading into memory, and we are taking we are using TensorFlow Keras here to load that pre-trained weights of that model. We are taking the pre-trained weights. Okay, pre-trained model we are taking. We are not doing any pre-training. We cannot do it because it is a very expensive, time-taking process. We do fine-tuning with the small data set we had, that disaster tweet data set, which had labeled disaster tweet or not value, just a binary classification. This is the model we represented here, okay, loaded into memory. We do a fitting with that data, and these are the metrics that we get. This is, you have the accuracy curves here, loss curves also here for training and validation sets respectively. So essentially, that is how you do or work with BERT. Okay, you use you take and load it out from Transformers library. You have the pre-trained library here. You use TensorFlow Keras, take TensorFlow Keras and load it into the memory. And then what you essentially do there is you call the fit function of TensorFlow Keras, and then you do the fit model fitting or the model train. Okay, and we did that in this here in this notebook by using a sample disaster tweet dataset. Okay. Okay. Let's move on. Let me share my entire screen one moment. I will reshare again so that we can switch between. Okay. So next, what we'll do here is we covered this disaster tweet classification, misinformation detection. What we'll do is we'll talk about RAG. Okay. See, the principle of RAG is nothing but two things: retrieve and generate. Before that, I will talk about why we are doing RAG. It is essentially a process of knowledge augmentation. Okay. See, these LLMs, as you know, LLMs has a lot of information. If you ask it, what explain the first law of thermodynamics, or explain the first law of Newton's first law, it will explain it. Okay, but that information is not current. And as this people working to cater to businesses and enterprises, right? See, they will have very specific documents, very specific information, maybe thousands and pages of documents related to a machine, maybe in a plant, right? A machine in a plant which is having, which is basically, let's take an industrial grinder which grinds its contents. You're talking about grinders costing millions of dollars, okay, of size, of capacity tons. Okay, you have this industrial grinder processing something. You have documents associated with that. What if something goes wrong? How can you get troubleshoot this machine, right? If it is a very newbie technician there, that technician will have issues. Even for experts to look up some information in the manual of associated with these assets or with these machines, you would need to scour through thousands and thousands of pages of text, and that whole time to repair, right, will be very high. Okay, so in these sort of situations, or in any situations where you need to answer questions from data, we have to augment these LLMs. We can use LLMs. LLMs won't know the specific data related to these machines. Okay, what we do is we augment the knowledge of these LLMs by using this process called RAG. Okay, so essentially, RAG is nothing but a zero-shot way of augmenting the knowledge of your LLMs. LLMs have the linguistic ability. Okay, you are essentially what you're doing here is you're taking let's take a machine which knows how to understands language very well. You're giving it a bunch of books, okay, and asking it questions. So these LLMs will go through these books and answer questions. As humans, we will take a lot of time to read books, but LLMs can go through thousands of pages in a couple of seconds. Okay, that is essentially the difference. The way that we do this whole process of RAG is in two steps: retrieve and generate. I initially what we do here is we identify and extract information from something called a vector DB, where we have stored that whatever manuals or documents we talked about, right, in vector form or as embeddings. It is same as the embeddings we talked about in the text embedding step in transformers. Okay, it's very similar, but what we do here is we do a sentence, or we do something called a sentence embedding. Okay, we don't embed each word by word in the vectorization process, but we model the entire sentence or a bunch of tokens together and represent it as a single vector. So that vector captures the conceptual meaning of that particular sentence or a paragraph. Okay, so we take these documents, we chunk it, we split it into chunks. Okay, we split if it is 1,000-page document, we split it into maybe 5,000 chunks. One page is split into five. Okay, each of these chunks, the concept is modeled by using an embedding model where we model the entire chunk, entire maybe paragraphs in that one page, right? Then what you do here is we do a retrieval process by using something called semantic search. It is nothing but a cosine similarity based search in that embedding space to get the closest matching vectors to whatever input that you're asking. Okay, if you're asking, hey, how do I what are the details of this error code 550 associated with this industrial grinder, if I'm asking this question, it basically captures it. What you do is you embed that sentence, whatever prompt that you gave, you do a semantic search, essentially a search operation on this vectors, on all of the vectors of that documents. You find the closest matching vectors which will contain information about this. Okay, and then what you do here is you give that information and the input question to an LLM. Okay, and then you ask it to answer that question. That is it. Retrieve and generate, these are the two steps. The benefits of this is because we get very grounded, very factual responses. It is very scalable. We can scale the data from 1,000 pages to 10 million pages or whatever you want, and you can use it within chatbots, within question answering systems. All of this you can do. Okay, these are the basic principles of RAG. Okay, now what we'll do here is we'll go through a quick case study of RAG where we create a quick chatbot. Okay, all right. So what we will do here is we will use Gemma model here, which is a model from Google. It's a lightweight, not a big model. I also wanted to introduce a smaller model here. Okay. So what we are do here is we will take a look at the libraries which we'll be using. We'll look at this library. For building the solution, we typically in the industry, we use LLM abstraction libraries such as LangChain, AutoGen, Crew AI. These are all LLM, Llama Index. These are all LLM abstraction libraries, where these libraries basically contain functions which will give you on your hands. It can do a lot of operations for you out of the box. Okay, instead of you writing every single step, it gives you functions which can do multiple operations. So whatever you are using here, LangChain is such a library which can do LLM operations, where it can do RAG, all of that. We just need to use the syntax of this library. We can do RAG. It also, the other benefit of that is it can connect to vector DBs. See, vector DB is nothing but a database which is efficient at searching vectors. Okay. So if you have a database which can search like a normal numerical or text information, that is your SQL DB, right? If you have a DB which is efficient or more optimized to search your embeddings, your n-dimensional arrays, right, and retrieve the chunk relevant to that, that is your vector DB, specialized SQL DBs, essentially. Okay. So what we do here is we load the data. It is essentially data from a website which contains, I will show you, which contains information about data science. Okay. It has a lot of information on data science, a lot of frameworks, a lot of ideas, technologies, a lot of algorithms. All of this is here. Okay. And what you're doing here is we are taking that, we are using this text splitter. As I said earlier, right? We split whatever documents we have into chunks. We have specify a size for it. And then what you do here is I'm using a specific vector in-memory vector DB called Chroma here, which I can simply import and create a vector DB. I don't have to set up the DB with more effort. You can also opt for setting up a better production-based DB, which I'll show in later slides. Okay, I will show a production-based DB. And here I set up the DB from the documents. I loaded the DB document DB with the documents, and then I created a retriever. So here I created a retriever, which essentially retrieves my nearest chunks by using similarity search. Okay. And then what I do here is I load the model from Google, right? It is from Google. So from Hugging Face endpoint, I load the model from Hugging Face endpoint. I created a chain, conversational retrieval chain, which essentially does the generation as well by combining the retriever and the LLM. So give the LLM and the retriever to this chain, it will create your conversational retrieval chain, which does retrieval and generation. So this RAG is done by using this class. Okay. And essentially, if you ask a question, what is data science? Data science is the ability to extract knowledge and insights from large and complex data sets. What is correlation? It gives you the answer. What is mean square error? It gives you the answer. See, this is telling you answers from your data, okay, from this data, whatever you loaded. Instead of this website, you can load documents. We will show how we can process documents as well in a better way. You can directly load documents, or you can do layout analysis as well, which we will see in a couple of minutes. Okay. This is a different use case. Okay. Now let's take a look at something very interesting. Okay. So this is an architecture in Azure where we use this framework, or we use a similar architecture to build our specialized solutions for our enterprise customers. So I will tell you about the stack very quickly. Okay. As the UI layer for the front end for your customer, every app will need a UI, right? Or a website, a web layer, which your customers can see, where you have the conversational insights, conversational interface, your insights, your inputs, your feedback to the solution, all of that is done in React. And we use a service called Azure App Services. It is a server-based web hosting service, managed service from Azure. Similarly, we have a backend here for that UI that is done, implemented in Fast API. Everything you see on the right here will be inside the backend, except this data layer. Okay. Everything here will be in the backend. And that is also hosted in app services. You have a security governance layer where you have custom Python modules by using certain libraries to filter out your personally identifiable content. Your content moderation is done. Your data anonymization, things like addresses, names, sensitive data, harmful data, not safe for data, all of that is filtered out to follow compliance standards of the industry to ensure that they don't get into any sort of legal trouble. Then you have an orchestration agent here. Okay, we are going into an agentic solution here where we employ agents which are nothing but self sort of self-working LLM based intelligent piece of software which has access to tools, and they use these tools to do specific tasks. Okay. One example of the task is your search and retrieval, your RAG. That could be one example. Another example is we can employ LLMs and give it a tool to communicate with SQL DBs. It will fire SQL queries on its own, get the right data for you according to the user's needs. Then you can have any sort of specialized AI or Gen AI based agents here, whatever task that you want. You can have ML models here packaged as an agent. See, you have a data ingestion processing layer here where you can do process different types of data, like your speech data, if the user is giving speech data, your audio data, that is your speech data, right? It does speech to text for your solution to work. You can have image data based ingestion so that you can embed that and do search and question answering on images. All of that can be done. Now you have your, see, all of this uses different services, managed AI services in Azure, like document intelligence for document processing. OCR is done by using that, custom vision for visual analysis, such features. Your AI speech for speech related tasks, all of these managed services are leveraged. As LLMs, we use the LLMs from Azure OpenAI service. They are managed, more secure in comparison to other offerings, and as part, it comes as part of AI Foundry. As frameworks, we can use LangChain or AutoGen or LangGraph, and we can also use custom LLMs from Azure Machine Learning Service in Azure. Okay, we get custom LLMs. Now you have the data layer, which stores all of your configuration data, all of your process data. Some of it is stored in SQL, some of it in NoSQL based Cosmos DB. Some of the all the vectors are stored in dedicated vector DBs. Like Azure AI Search is a managed vector DB from Azure. You have VV8 also, which you can use. You can have graph databases also here. You can store documents within Azure storage accounts. Raw documents can be stored here. Now, this is an example of a actual use case implemented for a customer. Okay, and this is how we leverage managed services to scale your applications and solutions for your customer and give them a very good solution. Okay. Okay, we'll move on to a very quick case study where we do agentic RAG. That is the last end of our session. I will take extra 5 minutes. I think we are over time, 2 minutes over time, but then I won't take more than 5 minutes. Okay. So essentially, here also we are using this framework called LangGraph. It is a framework from the same LangChain team, and what we do here is by we are making using this framework we can make agents by using a graph graph based methodology. Okay, we make agents by using by building graphs. And the way we build agents, see here in this solution, what we are doing here is we are taking PDFs and we are doing something called layout analysis. See, as you know, if we extract text from PDF simply, just get the text from it. There is no order for the text. We don't know where the text is from in a page. All of these problems exist. See, a PDF can have multiple columns. If you have worked on papers, your papers can have two columns, right? And on the top, you have your abstract. See, it is in the middle of the whole section, or sometimes on the left. You have different templates for different, what do you call, different journals and different, publishers, right? So all of those PDFs follow different patterns. In PDFs, you can have design elements, maybe in some documents. In PDFs, you can have images, tables, all of this, right? How do you tell your LLM that this is a table, this is an image, this is a header, footer, these are designs, it's a two-column PDF, all of that. For this, what we do here is we use something called a document processing and a layout analysis model. This also does OCR if your model or your solution, if your document has just a photo. If you take a photo of your Aadhaar card, you cannot search in that photo, right? So to convert your name, if it is my name Sri Vishnu into SREE, those characters, you need to do OCR. Okay, optical character recognition. That is also done by using this model. We are using a model called Docklink here, which does OCR and layout analysis. Okay, and shortly after this, in the solution, we do the splitting, all of that. We use Chroma, again, the same vector DB mentioned earlier. And we build an agent essentially by providing it with some inputs. okay, providing it with some input prompts, which mentions its duties. And we create a tool essentially, which will help us to retrieve inputs. Retrieve here, essentially, we are retrieving blog posts. We create a tool which will be able to retrieve relevant information by using semantic search. For RAG, we create a tool. And what you do here is we have an assistant agent which will be given this tool, and we'll ask the assistant agent, hey, you're an assistant agent. What your duty is to answer questions. Okay. From the retrieved context which will be provided to you, answer the question. That is what you're telling. Once you do this, you essentially are creating an agent which can use that tool. Okay, we'll pass in that tool later to one of the functions, and it will be able to use that tool to perform a task, and autonomously it will be able to answer your questions. So the reason why we use this whole way of doing things is called agentic AI, where you give a tool to an autonomous function where it will be able to autonomously act and then basically do some tasks. That is called agentic AI. The main benefit of this is that it will be able to autonomously and very flexibly do your task. It has memory, so it will be able to in a better way solve your task in comparison to non-agentic solutions. Okay, and it can handle very dynamic situations. Let's say the user is interrupting and asking some other things. User is asking very different things from very complex questions, right? Rather than doing what task it is assigned to, it can do this. Now, in the previous architecture, we saw something called an orchestration agent, right? Here the solution will be able to, by using agentic AI, it will be able to choose what task it should do based on the input from the user. So the orchestration agent is like a supervisor in a company. It will tell its employees, you do this task, you do task A, the other employee does task B. Similarly, orchestration can identify what needs to be done, what all tasks needs to be planned out. It will assign the task to its sub agents. The sub agents does the task, it will give it back, give the answer back to the orchestrator where it will answer the question. Similarly, we created a tool here. Okay, in this code, I'm not going through it. We created a tool which can solve math problems. So I created an agent which can search documents as well as solve math problems. And we created a supervisor agent. And what we do here is we can give a question to this solution. If you ask a math question, it will assign the task to that math agent, and then it will solve it. If you give it a document search question, it will assign the task to a document search agent, and it will give you back the answer. If you give a task to the solution where it requires solving a math problem as well as getting some information from documents, maybe some related information, it will assign the task to both these agents, solve it, and then give it back to you. That's the magic of agentic AI solutions. Okay, that in turn winds up our session. So I will summarize this particular use case where we use this ChromaDB was used, LangGraph framework and LangChain was used. ChromaDB was the vector DB. We implemented an agentic architecture by implementing an agent as a graph, and then that agent has these functionalities, whatever we mentioned, right? So, and also final thing, first thing that we did was to process the documents, to do document processing and layout analysis, where we understand the layout of PDFs, whether it has two columns, one column, images, text, all of this gets processed accordingly, and it gets given to the LLM accordingly, so that the LLM can understand these elements in PDFs better. Okay, just like we are reading it, we know columns, we know images, we know tables. LLMs don't understand that directly, so we make a component to make LLMs understand that. So that is also done. So we use a document layout analysis model, and that is how we implemented this solution. So that concludes our solution. And yes, so I will give a message to all of the participants. So the road ahead, right, is filled with AI, Gen AI, and ML. AI is not going anywhere, like I mentioned at the beginning. So it is up to you to innovate. It is up to you to learn and morph your students and create transformations in this area, so that all of you guys. I hope all of you guys are able to come up with very innovative solutions, maybe papers, and you're able to guide students to achieve their goals, maybe transform the next generation of people. in this area. Thanks a lot. Thanks a lot for your time. I hope you had a good session. I hope you got a lot of insights and a lot of inspiration. Thank you. Also, for anything, feel free to reach out to me. This is my LinkedIn. Feel free to reach out to me. Okay. So if you have any questions, maybe if you don't have any questions, feel free to drop off. But then if you have any questions, anything you would like to discuss, I shall stay back for some more time and I shall answer your questions. Feel free to ask.
Participants, if anyone having any questions, they are free to ask, or they can also ask your questions in the chat board itself. On behalf of Computer Science Department, I extend my heartfelt gratitude. Your expertise, clarity, and engaging presentation have truly added immense value to this FDP, sir. We deeply appreciate the time and effort you have dedicated to sharing your knowledge with us, sir. As a gesture of our respect and appreciation, we are honored to present you with a certificate of appreciation. Thank you once again for your valuable contribution and for gracing our program with your presence. We look forward to more such inspiring interaction in the future, sir.
Thanks a lot. Thanks a lot for the appreciation. Thanks a lot to everyone. Hope you had a good learning experience. Thank you and happy learning. Thank
Thank
you.
you, sir.